Hello everyone, welcome to the next session on ANSYS Workbench tutorials. In this session, we are going to analyze a curved surface for hydrostatic forces on it. Now we are going to actually analyze this body, which is a part of an experimental setup of fluid mechanics lab. This setup is basically used to calculate the hydrostatic forces which are applied on the body. The body can be partially or fully submerged, and this is how the setup looks like. You can see here, this is a curved body which is supported on the left hand side with the help of weights, and on this small rectangular surface that you can see, some amount of water or say sand or some stone whose weight is known, that can be used to just balance out the two sides of this structure. This may or may not be required based on your balance on both the sides. As you can see that there is a central fulcrum created, and on these two sides they are going to just swing based on say how much water you apply here, and you need to add some weights to balance it out. Initially, for creating a simple balance without any water in this, we have created this structure to say adjust the balance and bring it to a straight level with the help of some water in this zone. So this weight will not be initially there. This will be added once this is balanced and you start adding little water. This bends down, and to bring this back to its position, you will add weights equivalent to the weight of the water that is applied here. And the maximum level of water that we are going to apply is still here. So we will see certain formulas that are used in theory. As you know, for calculating the hydrostatic forces, there are two basic components for a curved surface. One is along the x-axis and the other is resolved along the y-axis. It is actually a resultant force which acts on this curved surface. So this resultant is resolved in x and in y direction. So along the x-axis, when you calculate this force, theoretically, you say that it is the total pressure force on the projected area of the curved surface on a vertical plane. So suppose if this is a curved surface, the maximum projected area is up till here. This is the projected area, and the other side is a rectangular surface. So this is a vertical plane, and on this surface, whatever force is exerted along the x-axis, that is the force exerted along the x-axis for the curved surface as well. So the formula stands rho g a h bar. And when I talk about the y component, it is a weight of water supported by the curved surface up to free surface of water. So whatever weight of water is supported here up to the free surface of water, we are going to calculate the force acting in the y direction as rho gv. We know weight can be written as m into g, and mass in itself is rho into v. So this becomes rho vg or rho gv. So these are the two formulas which you can use for numerical calculation. And as far as this apparatus is concerned, when you are doing it practically, you add some water, this goes down, and equivalent amount of weight is applied, and you can just equate and you can figure out the forces. And as far as the x direction forces are concerned, practically if you see, it is not technically possible to calculate, and it is actually not there. The reason being, this is a fulcrum and the both sides of forces along the x-axis are balanced, and that is how you can maintain a straight level for this entire apparatus before starting it. So along this fulcrum, the x-axis forces generally get cancelled out, but the y direction force is what is important for us, and that is what we can measure using this apparatus. So we are going to see that. Now I have already made a calculation for this. This formula is something which you already know for calculating the center of pressure for this apparatus. It is Ig plus AH bar square upon AH bar, where A stands for the cross section area of the rectangular surface, that is the projected area. As I told you, the curved surface will have a projected rectangle over here, and h bar is the position of center of gravity from the free surface of the liquid, and ig is the moment of inertia of the area about the axis passing through the cg of the area and parallel to the free surface of the liquid. So moment of inertia for this rectangular body is actually bd cubed by 12. So based on how much is the breadth and how much is the depth of water in this curved surface, you can calculate the value of ig. So that's a very simple calculation for h bar numerically. So you can do these three calculations, which I have done for this height of water, and this is the breadth, or this is the thickness of this entire curved surface, that is 6.6 centimeter. This material that you see is acrylic, so we have obviously given some thickness to it. It is 1 centimeter in all directions, and from this point the radius, if you measure this inner radius, is 9 centimeter, and from here this outer radius is 18 centimeter. So these are the two dimensions that are required for doing ANSYS analysis as well, because we need to create the geometry. So we have measured the mass of water by taking that much amount of water in the curved surface by measuring it with the help of beaker, and then I converted it to weight by multiplying with 9.81. So this is the weight of the water, 2.45 Newton, and this is the depth of immersion, that is how much amount of the surface is immersed in water. So this is the height of water. This h is nothing but the height of that entire rectangle. So this is what you need to know. Now for calculation, this is very simple by using rho g a h bar, and for fy by using rho g and volume. This you must have already studied in fluid mechanics subject. So we have just done the calculation that way. Got the resultant value as 2.42 Newton, as you can see here. So I will try to check out these values. Now there's only one correction here, that this value of area is height into depth, and the height of immersion is only 0.064. So in case you're calculating, this is 0.064, and the breadth, as we know, is the total water filled up. So it is 0.066. This is correct. And here also you will just take half of this height, that is a position of CG, because the height is the height of the rectangle. So just take here 0.032 as the value, and you will get some answer here. So just check out this value, and this is not the correct one that we have here. This value is correct. It is 2.08 Newton, and this R is 2.42 Newton. So for this depth of immersion, we got certain values of Fx, Fy and R. I just want to check out these values using ANSYS. So we will go to ANSYS and we will double click on static structural. I'll first go to engineering data, and I'll change the material of this curved surface to acrylic. So I will enter here a material which is acrylic because it is not there in the library, and I also need to give certain values to it. So the first value that is required is the density in kg per meter cube. So we have figured out a website for figuring out the values of the material acrylic. So the first thing that you see here is the density. The range is from 0.942 to 1.19 gram per centimeter cube. You have to convert this into kg per meter cube. So this becomes 1190. I'm taking the highest value. So we'll just enter the value here, 1190 kg per meter cube. Next, I'll have to give a value of isotropic elasticity. For that, I need to provide the value of Young's modulus. We'll check here. The mechanical properties have also been given. Now, I will link this website for you so that you can use it for figuring out these values by yourself. So here you can see the modulus of elasticity is given in the range of 0.042 to 3.3 gigapascal. I'm using the highest value, 3.3 gigapascal. So I will enter 3.3 E9 Pascal. Next, I need the value of Poisson's ratio, that is also given on this website. It is from 0.37 to 0.43. I'm using the highest value 0.43. So I have given all the material properties required. The only thing required is the temperature here. So just give 22. That is the standard temperature. Next I'll go to project and update projects. Next I'll go to geometry and right click. I'll go to new design modeler geometry. Units I'll choose centimeter, XY, look at. I'll go to sketching. I'll first choose circle and draw two circles. Then I'll go to line and I'll draw a line here and a line here. Next I'll go to modify and use trim option. I'll trim out the extra portion. Now I'll go to dimensions and give the radius. As we discussed, the inner radius is 9 centimeter and the outer one is 18 centimeter. Next I'll go to modeling and I'm going to extrude. For sketch, I'm going to add material and the depth, as I told you, is 6.6 centimeter, but that is excluding the thickness of the acrylic. So it will be total of 6.6 plus 2 centimeter. So a total of 8.6 centimeter and generate. Next I'm going to use the thin option. I'll select faces to remove and I'll select the top face. Inward, I want 1 centimeter as a thickness, so I'll generate. So that's a very simple way of creating a curved surface. Now that is done. So I'll go to model and double click on it. I'll first go to geometry and change the material to acrylic. Next I'll go to mesh. I'll choose sizing as fine and update. Next I'll go to static structural and right click and insert fixed support. This is a surface which has to be applied as fixed. And I'm going to insert hydrostatic pressure on all the internal surfaces. So I'll press Ctrl and select the inner surfaces. Apply. I'll give the fluid density in the units of meter. So this will be 1000 kg per meter cube, as I'm going to test it for water. I'll change vector to component and along the y-axis I'll give the value as 9.81 meter per second square. Now for the x, y and z coordinate, I will click on this option of location and I will choose this h and apply, because that's the value that I know. So I want to calculate at a depth of some value. So I will just change this y coordinate and I will try to get the answer. So that is 9 centimeter, if you know. So I'll just change this units to centimeter again. This is 9 centimeter. The difference between 9 and 18 is 9. And 1 and 1, 2 centimeter gone. So just 7 centimeter remains. Okay, so depth of immersion is 6.4 centimeter. That's what we have measured. So I am going to give this value. So it's approximately 0.6. So let me take this as minus 9.6 as the value. I will now insert deformation total. I want to see the stress. I want to see the strain generated over this body. And the most important thing that I want to see is by going to the probe tool, I want to see the force reaction on the fixed support so that I can get the x and y forces on this rectangular surface. So I'll go to solution and solve. I'll go to force reaction. This is giving the values in time. So I'll change the units to meter such that I get the answer in Newton. Now you can check that it is giving certain values. So this is at a height of 9.6 centimeter. I'll just change the units to centimeter again. So it is 18 minus 6.4, that is 11.6. So it's minus 0.116 meter, at which I want to calculate, solve. So you get some approximate values in the y direction and the reaction is 2.65. If you check this, you will get the y direction value as 2.08 Newton and reaction as 2.42 Newton. Now these are close to the values that I have obtained here. Obviously you will not get the exact values because whatever value you get numerically is the exact value, and through the use of software what you get is a close answer, which just helps you understand that you have got a close by value. But what we need to exactly figure out is this value of y and this reaction force, which is something that we are able to tally. And through this experiment also, we are actually trying to mainly figure out what is the hydrostatic force on the body. So when you use this formula for solving, you will get that value. Now, one more thing which I can tell you from this analysis is that the ANSYS analysis is three directional. So what is happening is it is taking into consideration of z direction force, which we have not taken into our calculation. So that is why it is possible that this value which I obtain over here, please change this value to 0.064 as I mentioned before, and this value to 0.032. You will get a value of 1.32 Newton. So that's a correct answer. So when we solve in this fashion in the class, we generally use two components, and hence these two have to balance out and figure out the value of R for us. But when we use software, there are three directional forces. So whatever force you must have got in the x direction gets somehow balanced with the z direction force. And that's how you can say that this value of x is not wrong. It is just that it is one component of three components here. But when we solve in class, it is a complete two-dimensional analysis, and hence this x value is a little higher over here as compared to the value that you see here. So these values are actually adjusting themselves to give this resultant value, which is again close to the value that we have obtained by using numerical method. So this technique is something which you can use for analyzing an experiment. You can see how simply the experiment gives you the value by just adjusting the two forces. So when you check this weight, say it will be 2.45. That's what we figured out. That you can see here. But when we went for this y directional force, it was 2.08. Now when you go to the software, you are getting 2.65. Again, very close to 2.45. So all these values are just giving you close by values. Obviously, numerical solution is two-dimensional. It is giving you a solution. ANSYS is three-dimensional. It is giving you another solution close to each other for y direction and resultant force. That is main objective of calculation. Please be careful. And when you use this experimental setup in the lab, it is giving you a value which you are doing by trial and error. Also, this fulcrum over here, this is a lever arrangement. It's like a seesaw movement. So when this lever is attached here, or this is a fulcrum here, at this point there could be some looseness of joint or some tight joint. So because of that, this weight adjustment could also give you some error in reading. So the most appropriate method generally used in research is the numerical method. Then you have these experimental results which you can use to tally your numerical results. I am giving you a third dimensional analysis here, that is of this kind of a software analysis which helps you prove that either your experimental solution is correct or your numerical solution is correct. So this is a research technique used, but be careful to give correct material properties to this surface. If you want, you can go to deformation and you can see the animation. The deformation that is occurring is actually very small. You can see an exaggerated value here. It is 2.242 into 10 raised to minus 7 meter. It's actually very less. And if you observe this, this is moving about this point, and this was always remaining fixed. So that's how I chose fixed over here, in case you have a doubt as to why this end is fixed and why not creating some imaginary point here fixed. It is not the correct way. So you can go to the equivalent stress and you can check. It is 718 Pascal. And this is the strain which is generated, 2.57 into 10 raised to minus 6. So it's again a very small value of deformation which is happening. Our most important result here is this X, Y, Z directional force and the total reaction force. And amongst that also, the Y force is most important because that's what we tally in the experimental solution, and the reaction and the Y direction force we tally with the numerical calculation. X direction force cannot be tallied in this way because X and Z direction is actually playing a different role in the software. So that's how you can analyze this curved surface. If you have any doubts, please write to me in the comment section. Don't forget to like, share and subscribe to the channel. Hit the bell icon for latest video updates. See you in the next session. Thank you.